This part of the lesson will deal with how the aeroplane's landing distance can actually be calculated. All aeroplanes will have either a pilot operating handbook or an aeroplane flight manual. The purpose of these manuals is to show not only how to operate the aeroplane, but also to detail the aeroplane's performance. Shown on screen is an example of the landing performance information. The example graph we will use is figure 2.4 on page 10 of section 2 in CAP 698. Always take a look at the associated conditions first, paying particular attention to the power and flap settings as shown here. Also notice that this graph assumes a runway which is paved, level and dry. If the runway conditions required for a given calculation are different, corrections will need to be made to the values that this graph will give. We saw these correction factors earlier. Notice this box here, which highlights the screen height speed for different weights. You may recall that the regulatory speed at the landing screen height is called VREF, and for a Class B single-engine aeroplane it had to be no less than 1.3 times the stall speed in the landing configuration, 1.3 VSO. A pilot must adhere to the VREF speeds shown here because they are the speeds which have been used to construct this graph. If a pilot were to deviate from these speeds, the required aircraft performance would not be achieved. Having looked at the various bits of information associated with the graph, let's now examine the graph itself. The left-hand carpet of the graph involves the variations in temperature and pressure altitude. This part of the graph accounts for the effect of air density on the landing distance. In the example, we will assume a temperature of 5 degrees Celsius at a given airfield, situated 4,000 feet above mean sea level. To use the graph then, move upwards from 5 degrees Celsius until you have reached the 4,000 feet pressure altitude line. Then move right until you meet the reference line, shown here. The next variable is mass. In our example, let us assume a mass of 3,400 pounds. From the reference line, we must move down using the sloping guidelines until we reach 3,400 pounds, as shown here. From this point, we go horizontally to the right until the next reference line. The next variable is wind. In our example, we will assume a 10-knot headwind. Notice, though, that the slopes of the headwind and tailwind lines are different. We therefore recognise that the 150% tailwind and 50% headwind rules that you learnt about in the General Principles for Landing lesson have already been applied. Travel down the headwind line until you reach 10 knots headwind, and then move horizontally right once more, up to the last reference line. Remember that the landing starts at the 50-foot screen height, so from this point on the graph we must move more up the guidelines to the end. The landing distance in our example then is approximately 1,350 feet from the 50-foot screen to the full stop. The landing roll, in other words the ground section of the landing, is just 860 feet. Let us now assume that the runway has a grass surface and that the grass is wet. Remember that both these variables cause an increase in the landing distance. Since the graph assumes a paved dry runway, we will have to make a correction to the landing distance for the different conditions. You may recall that grass increases the landing distance by 15%, or by a factor of 1.15, and a wet surface also increases the landing distance by 15%, or by a factor of 1.15. Our calculated landing distance is 1,350 feet. But correcting it for grass means we need to multiply this by 1.15 and again by 1.15 because the grass is wet. This now makes the landing distance 1,785.375 feet. Let us now assume the runway has a downslope of 1%. You may recall this would increase the landing distance by 5% or by a factor of 1.05. This now makes the total gross landing distance 1,874.64 feet. To comply with the regulations, you may recall that the landing distance must be within at least 70% of the available distances at the airfield. Therefore, multiply 1,874.64 feet by 1.43. This means that our landing distance available must be at least 2,680.74 feet. Hopefully, you are now able to work through the landing graphs for Class B single-engine aeroplanes and make the corrections to the graph for any conditions that are not accounted for by the manufacturer. If you need further practice in using the graph to increase the accuracy of the results, we suggest that you work through the example in CAP 698 on page 9 of Section 2, or use the questions on this CD, which test you on what you have learnt in this lesson. That concludes the section on Class B single-engine performance. The next section of aircraft performance will focus on the Class B multi-engine aeroplane.